Right now, about 1 million messages a second are moving through WhatsApp. 100 billion a day. You send one of them. It leaves your phone, and a fraction of a second later, it is on somebody else's screen. So where do they all pile up? They don't. Look at what the server, just a computer that answers other computers, actually keeps. 0. It hands your message to the person you sent it to, and then the server deletes it. Within seconds. Not your copy though. Your phone keeps that, and so does theirs. What disappears is the copy the server was holding, only ever to pass it on. Now size that yourself, at the real scale. 100 billion a day, 1 kilobyte each, is 100 terabytes every single day. 36 petabytes a year. All of it thrown away moments after it lands. Which leaves exactly one question. And this whole video is the answer. Where does a message wait when your friend's phone is switched off? Follow the message through every machine that touches it. It leaves your phone and arrives at a load balancer. That is one machine sitting out front. Its only job is to pick which chat server you talk to, and then to keep you on that same one for the rest of your session, because your open line only exists on that one machine. Behind it are the chat servers. This is where your open line actually lives. One of them holds hundreds of thousands of those lines at the same time. Now watch what it does not do. It does not write your message to disk. It drops the message onto a queue, a line that waits in, and answers you immediately. A storage service reads from that queue at its own pace and writes the message into the message database, a store that keeps data on disk. That is the whole send path. Now, 4 more things hang off those chat servers, and each one earns its place. First, a cache, a small, fast store kept close by that remembers which chat server every online person is attached to right now. Checking it takes microseconds. Asking a database would take milliseconds, and at 500,000 messages a second, that difference is the whole system. Second, blob storage, which just holds files with a content network in front of it that keeps copies close to whoever is downloading. A photo never travels down your chat line. Third, a notification service. It is the only thing here that can reach a phone with no connection open at all. And fourth, a presence service, quietly tracking who is online and when they were last seen. And one hop that almost every diagram leaves out. Your friend is very probably connected to a different chat server than you are. So the machine holding your line asks that cache where they are and forwards the message to the machine that is actually holding them. Only then does it go down their line. 10 machines, 2 of them chat servers, 1 message. So here is what the rest of this video answers. How your phone keeps a line open. How the server finds your friend. Where a message waits when nobody is there to catch it. And the 5 ways this breaks on a real network. Now the part that changes what every one of those boxes actually means. Before your message leaves your phone encrypts it. That means it scrambles the text using a key, and the key never leaves your device. Not a copy on the server. Not a copy at WhatsApp. So the chat server we just drew receives a sealed envelope. It cannot open. It can see who it is for and how big it is, and that is all. It hands the envelope on, and only the phone at the other end holds the key that opens it. Photos and video work the same way, encrypted on your phone before they are ever uploaded. So go back to that server, deleting its copy. It was deleting something it could never read in the first place. WhatsApp calls this end-to-end encryption, and it is the reason this design looks the way it does. Before a single box gets drawn, you write down the requirements. What the thing has to do. Freshers skip this and design a beautiful system that solves the wrong problem. Functional requirements are what it does. One-to-one chats, obviously, group chats, and WhatsApp's real limit today is 1024 people. Hold on to that number, because later you will see exactly what it cost to send one message to all of them. Messages for someone who is offline, kept 30 days and then dropped. Media, meaning photos, video and voice notes, sent, delivered, read, the ticks you already stare at every day, last seen. Non-functional requirements are a different thing. They are how well it does it. Under half a second when both people are online. Nothing ever lost because a chat app that occasionally eats a message is not a chat app. Billions of users keep nothing longer than you must, which you now know is the whole storage story. Survive a machine dying without anybody noticing. Now look at that offline one again. That is the hard one. It is easy to design for everyone being online. Real life is people on trains and dead batteries. Let us actually run it, because this is the part an interviewer really wants to see. 3 billion people have accounts. 2 billion of them open the app on a given day. And that is the number that matters, not the total. Say 50 messages each, which is modest for a chat app. That is 100 billion messages in one day, which is exactly the number we opened with. Divide by the number of seconds in a day, 86,400 of them, and you get 1.2 million messages every second. Now the average is the lie. Nobody messages evenly around the clock. At 4 in the morning, this system is nearly idle. Everybody piles into the same evening hours, so the peak runs 3 to 5 times higher. Build for the average, and you fall over at 8 in the evening, which is exactly when everybody is watching. And be honest about these numbers. They are a sizing exercise, not a leak. Another design will pick 20 billion and get double. The real WhatsApp moves 100 billion a day. What matters is the method, not the digits. Now the part that costs money. 200 million people are connected at once, at peak. Not typing, just connected. Every one of those open lines holds memory on a machine somewhere, awake, doing nothing. Now, what does all that traffic actually add up to? Far less than you would guess. 100 billion messages a day, at a kilobyte each, averages out to a bit over 1 gigabyte a second. A single fast drive could keep up with that. So bandwidth is not the thing that makes this hard. The memory is. 200 million little pieces of state sitting in RAM and almost all of them doing nothing at all. So how many machines? A textbook design assumes about 200,000 open lines per machine, which puts you at 1,000 of them. WhatsApp did far better than that. They tuned a single box past 2 million connections and ran roughly 150 chat servers, holding about 1 million phones each. Start with the obvious way. Your phone asks the server every couple of seconds, "Anything for me?" Almost always the answer is no. Notice what is missing. The server can never start the conversation. It can only reply. That is how the web normally works. You ask, it answers, the line closes. And if a message lands just after you asked, it sits there for the full 2 seconds before anyone tells you. 2 seconds does not sound like much until you are mid-conversation. Multiply that by millions of phones asking about nothing, and you are burning bandwidth to be told no. Long polling is smarter. The server holds your question open until something arrives. But every message still needs a fresh handshake. The back and forth two machines do before any real data moves. At this scale, your servers end up managing connections instead of delivering messages. So here is the fix, and it is almost embarrassingly simple. Instead of asking again and again, you open one line and leave it open. That is a WebSocket, one connection, held open, that either side can top down. Watch what happens to the picture. All those repeated requests collapse into a single lane that runs the whole length of the conversation. The handshake happens once when you open the app. After that, there is no asking, no reconnecting, and no waiting for the next poll. When a message arrives at the server pushes it straight down that open line in a few milliseconds. And it works both ways at the same time. You send on the very same line you receive on. Now the honest cost. That line has to be held open even when nothing is happening, and holding it costs memory on the server, which is exactly the bill we counted earlier. One honest note. WhatsApp's own app does not literally speak this. It uses a custom protocol, its own agreed way of talking, built on XMPP. And WebSocket is what the web client uses. The shape of the idea is identical, and WebSocket is what you would reach for today. An open line has a problem you would not think of. It can be open and dead at the same time. The phone walks into a tunnel, or the app gets closed in the background, and nothing tells the server. From the server's side, the line still looks perfectly fine. So the client sends a heartbeat, a tiny ping, typically every 30 seconds, and the server pongs straight back. That is the entire message. No content, just proof of life. Now, if the server hears nothing for about 60 seconds, it stops believing. It assumes the line died and closes it. And that matters more than it sounds, because a dead line costs exactly the same memory as a live one and delivers nothing at all. Multiply that by 200 million, and you can see why nobody wants zombie connections piling up. So, how does your phone know your friend is online? Here is the wrong answer first, because it is the one everybody reaches for. Every time somebody's status changes, tell all of their contacts. One person with 500 contacts comes online, and that is 500 messages for nothing. Multiply that by 200 million people, and presence alone would cost more than the actual chatting. So it is done lazily instead. Their phone sends a heartbeat, and the server writes one key. This user is online, expires in 30 seconds. Every heartbeat pushes that expiry back out. Nobody is told anything. Then, when you open their chat, your phone asks the question once. If the key is still there, they are online. If it quietly expired, they are not. And the moment it was last written is exactly what last seen means. Your friend's line is open to exactly one machine out of hundreds, and the machine holding your line has never heard of them. So how does it find out? There are two pieces. First, where a user lands is not random. Their ID is hashed onto a ring, and they belong to the first server clockwise from that point. Every machine can work that out on its own, with no lookup at all. Second, a session row, one per connected user, saying which server is holding them and over which connection. That lives in Redis, and it expires by itself unless a heartbeat refreshes it. Why Redis and not the database we already have? Because this lookup runs on every single message. Redis answers in microseconds. A database answers in milliseconds. At 500,000 messages a second, that gap is the difference between working and falling over. Here is that hop up close. Your line is open on one machine. Your friend's line is open on another one entirely. So those two machines have to talk to each other. The first one takes the session row. It just looked up and forwards your message to the machine named in it. There are three common ways to do that, and they fail differently. A direct call between the two servers is the fastest. But now, every machine has to be able to reach every other machine. A publish and subscribe channel is far simpler to wire up, but it keeps nothing. If the other side is not listening at that exact moment, your message is gone. A queue is a few milliseconds slower, and it survives a server dying halfway through. So anything that must not be lost goes through the queue. And then the second machine does the easy part. It pushes the message down a line that is already open. So here is where the message waits. Your friend's phone is switched off. The lookup comes back empty. There is no machine holding them, so there is nothing to push to. The message does not bounce, and it is not thrown away. It gets written down and marked undelivered. Now here is the neat part, and it is simpler than a queue. The server keeps one number for each device, the ID of the last message that device actually acknowledged. Think of it as a waterline. Everything below that line, the device already has. Everything above it, the device still owes. So when the phone finally comes back, it does not ask for everything. It says, "Here is my waterline," and the server sends only what is above it. And if nobody ever comes back, undelivered messages are kept for 30 days. Then they are deleted, whether they ever arrived or not. Watch what happens as each message is handed over. The phone acknowledges it, and the server deletes its copy. Not later, not on a schedule, right then. So follow that all the way to its conclusion. If the server drops every message the moment it lands, then where is your chat history? It is on your phone, in a small database inside the app, on your own device. And if you have backup switched on, A second copy sits in your own cloud storage, your Google Drive or your iCloud, which belongs to you and not to WhatsApp. That is exactly why a new phone starts empty until you restore a backup. The server has nothing to give you. And one thing worth separating, because people mix these up constantly. This is not the disappearing messages feature. That one removes messages from the chat on everybody's devices after 24 hours or 7 days or 90 days. What we are describing is the delivery plumbing underneath, and it has always worked this way. But there is a gap in everything I have just described. If the phone has no line open, and it is not going to open one until somebody taps the app, then how does anyone know a message is waiting? Nothing inside our system can reach that phone. This is the one place the design has to hand off to somebody else entirely. Apple and Google each run a service whose whole job is waking up apps on phones. On iPhone, that is APNS. On Android, it is FCM. Our server sends them a small notification and they wake the phone. And notice what that notification cannot contain, the message itself. That is encrypted, and Apple and Google do not have the key. So the phone wakes up, opens its line, says, "Here is my water line," and pulls the message down exactly the way we have already seen. Stop for a second and look at what we have. Your phone holds one line open, and a heartbeat keeps it honest. The server knows which machine is holding anybody, because the ring says where they should be, and the session row says where they are. And when nobody is there to catch a message, it waits behind a waterline until the phone comes back. That is a working chat system. It is also a chat system that has never met a real network, because everything I have shown you so far quietly assumes that things arrive exactly once, in the order they were sent, and that machines stay alive. Not one of those is true. So here are the 5 ways this breaks, and what each one costs you. One of them sends your message twice. Break 1. Your phone has been off for 2 hours. It wakes up and break 2, and this is one you have actually felt. You hit send. The message gets to the server writes it down, and the acknowledgement starts coming back to you. And then your train goes into a tunnel, and that acknowledgement never arrives. Now think about what your phone knows. It cannot tell the difference between a message that never got there and an acknowledgement that got lost coming back. Both look identical from where it is standing, so it does the only safe thing. It sends the message again. And now the server has it twice, and your friend reads it twice. The fix is small, and it lives entirely on the sending side. Your phone attaches its own ID to the message before it ever leaves, a unique string it made up itself. On the retry, that very same ID arrives. The server looks it up, sees it already has that one, throws the copy away, and simply resends the acknowledgement that went missing. Retry as often as you like. It only ever lands once. Break 3. You send 2 messages, one straight after the other. See you at 8. Then actually make it 9. They leave your phone in that order. But between you and your friend, they may take different paths. A retry on one, a slower queue for the other, and they can arrive swapped. Now your friend reads, actually make it 9, then see you at 8. The same 2 messages and the opposite meaning. There are 2 fixes and you want both. First, the message ID itself begins with the time it was created. So sorting by ID sorts by time. The order travels inside the message instead of being guessed from the order it turned up in. Second, The queue is split by who the message is for. Everything headed to one person goes down a single lane, in sequence. Different people are handled in parallel. One person's messages never are. Break 4 looks like a performance win and is actually a data loss bug. Remember that the chat server answers you immediately, before your message is written to the database. That is what keeps it fast. But think about what happens if that machine dies in the half second in between. Your phone is holding an acknowledgement. It believes the message is safe. And the message does not exist anywhere at all. So here is the rule, and it is absolute. Never acknowledge anything until it is somewhere durable. Which sounds like it undoes all the speed. Except that the queue is durable. Writing to the queue is a real write to disk, copied onto more than one machine, and it takes about a millisecond. So the order is onto the queue, then acknowledge, and then a storage service drains that queue at its own pace and writes each message into the database. The sender never waits for the slow part, and nothing is ever acknowledged that could still vanish. So why not put all of this into one database? Because these are two completely different shapes of data, and they get asked completely different questions. Users, groups, and who belongs to which group. That is, relationships. A person joins a group. A group has members. Delete an account, and every one of those links has to stay consistent. That is precisely what a relational database is built for. So Postgres, or something like it. Messages are the opposite in every way. Billions of writes a day, almost never edited afterwards, and really only one question ever asked of them. Give me this conversation's messages in time order. So they go somewhere built for heavy writing. Typically, Cassandra, a database made for exactly this. Every message in one conversation is stored together and already sorted by time on disk, which makes that one question nearly free. And because a conversation can run for years, it is usually split into buckets by month, so no single chunk grows forever. Those little checkmarks you have looked at 10,000 times are not decoration. Each one is a separate message traveling back to you, and they mean three genuinely different things. One tick means the server has it. That is all it means. Your friend's phone could be switched off in a drawer. The server simply took it from you. Two grey ticks means their phone actually has it now. Their device received it and sent back a confirmation of its own. And two blue ticks means somebody opened the chat. Their phone sends back the list of message IDs that were just put on screen. 3 signals, 3 separate trips back. And this is exactly why group ticks behave the way they do. The server tracks delivered and read separately for every single member, and you only get 2 blue ticks once the last person has opened it. Groups. A group message does not carry a recipient at all. It carries a group ID, and the server works out who that means. Now, the obvious way to do this with end-to-end encryption is brutal. Encrypt the message separately for every single member. In a group of 1,000, that is 1,000 encryptions on your phone for one message you typed. So it is done differently. Once, the first time you send to a group, your phone creates a sender key and delivers it privately to every member. That part is expensive and it happens once. After that, you encrypt the message a single time with that sender key and hand one copy to the server. The server fans it out and everybody can already read it. And the server has a trick of its own. It batches by machine. Say 3 of those members happen to be sitting on the same chat server. It sends one message to that server with 3 names on it. Not 3 separate messages. That is why a group of 1,000 is possible at all. Media. A photo is about 2.5 megabytes. A text message is about 1 kilobyte. So a photo is roughly 2,000 times bigger than everything else on that line. Push that through the chat server, and one person sending holiday pictures blocks the machine that is holding 100,000 other people's conversations. So it does not go that way at all. Your phone encrypts the file first on the device before it goes anywhere. Then it uploads the encrypted blob straight to a storage bucket over a completely separate connection. The chat server never touches it. What actually travels down your chat line is tiny. a link to that file, a key to decrypt it, a fingerprint so the other side can check it arrived intact, and a small thumbnail so you see something immediately. The bucket only ever holds the encrypted version. Whoever runs that storage cannot open it either. One more thing that quietly changes all of this. You do not have one device anymore. You have a phone, maybe a laptop, maybe a tablet. And here is the part that surprises people. WhatsApp does not treat those as one account with one key. Every single device gets its own identity key, created the moment you install it. The server keeps a map from your account to all of your device identities. So when somebody sends you a message, their phone first asks for your device list. Then it encrypts that message separately for each device you own. 4 devices means 4 encryptions sent 4 times. That is called client fanout. And it is the reason your laptop keeps working when your phone is switched off in another room. And when you link a brand new device, your existing phone packs up a bundle of your recent chats, encrypts it, and hands it across. The server carries the parcel. It never sees inside it. Break 5. And this is the one that actually happens every day. Machines die. They also get deployed, restarted, and scaled up and down all afternoon. So nothing in this system can have an address written into it. Instead, every chat server writes its own row on a board when it starts up. Here is my name, here is my address, and here is where you can ask whether I am still alive. The load balancer never guesses. It reads that board, and it watches it for changes. Then, something checks each server every 10 seconds. 3 failures in a row, and the row is struck off the board. Traffic stops going there within seconds. And notice what happens to everybody who was connected to that machine. Their lines are simply gone. Their phones notice, reconnect, and land on a healthy server. And those stale session rows from earlier, nobody has to clean them up. They expire on their own. Now, the honest cost. That board is one more system you have to keep alive. So how did the real thing actually get built? Not quite the way we just drew it. WhatsApp ran on Erlang, a language designed in the 80s for telephone switches, on top of FreeBSD. Both picked for the same reason. They are extremely good at holding an enormous number of connections open while doing very little with each one. And the database? Not Postgres and not Cassandra. An in-memory store called Amnesia, built into Erlang itself. About 2 terabytes of RAM split across 16 partitions, holding roughly 18 billion records. And here is the part that ties this whole video together. What it held was messages in flight, not an archive. A store built for things passing through rather than piling up. And here are the numbers that make engineers stop and read them twice. 2 million connections on a single machine. In testing, they pushed one box past 2.8 million. 50 billion messages a day. And the team running all of it, at the point Facebook bought them, was 32 engineers. Not 3200. 32. That is not a trick, and it is not magic. It came from ruthless simplicity. No ads, no feed, no features that did not serve sending a message. Every idea in this video is real. But the reason it fitted onto so few machines and so few people is that they kept saying no. So, back to where we started. 100 billion messages a day, and the server deletes it the moment it has been handed over. Now you know exactly why, and exactly what has to be true for that to work at all. Your phone holds one line open, and a heartbeat proves it is still alive. A ring decides which machine you belong to, and a session row remembers where you actually are. When nobody is there to catch a message, it waits behind a waterline until your phone comes back and says how far behind it is. And every bit of it is encrypted, so the machine carrying your message could never read it anyway. If you take one thing away from all of this, take this. The hard part of a chat system was never the sending. It is everything that has to happen when the network refuses to cooperate.